would think. You probably remember standing waves on strings. We talked about these and that there's some relationship between lambda and L, length of string. And for the first wave, what is it? Lambda equals 2L. And we can go down through a whole series of waves that are created, and basically it's this picture which appears in your notes and your book and all over the place. Fantastic. You all understand that. We don't need to say a whole lot more. You can calculate the frequencies for any of those waves. So if we're now talking about musical notes, so for instance, what's called concert A, which apparently professional orchestras tune to, is 440 hertz. It's pretty dead on 440A. Well, we can take a given string, we can take the speed of sound in air, which is usually given depending on the temperature and everything else. 343 is a number you commonly see, 343 meters per second. Anywhere from 340 to 345 are things that you'll see. And based on the relationship V equals F lambda, if we know the frequency we want, and we know the velocity we want, and we know that there's a relationship where lambda equals 2L, well, by golly, we can figure out how long a string will produce a given tone, which is kind of handy. Now, this does not factor in tension. And how many people here have ever touched a guitar? Okay. If you haven't touched a guitar, you have homework. You need to find somebody with a guitar, go over to their house, and touch it. So you know that you change the tension on the strings to tune. This equation does not factor in string tension. And frankly, I'm not enough of a physicist or a musician to really answer how that fits in. I would love to know. So I would love... Do I have any guitar players? Like serious guitar players? Okay. Semi-serious is fine. You know, dorking around in your bedroom with your guitar is perfect for this. See if you can find anything on tension and this relationship. So because of this whole relationship, we can we solve for F. So F is equal to velocity divided by lambda. And for the first harmonic, for the first standing wave, 2L is equal to lambda. So what we end up with is the frequency is equal to the velocity of sound in air divided by 2 times the length. And then we can solve that for length. So we can solve for the frequency for a given length, or we can find the length of string that we would need. Okay. You remember this picture, I'm sure, from standing waves. And they get tougher and tougher to draw. So we remember the relationships, lambda equals 2L, lambda equals L, lambda equals what? What is it? 2/3 L. Okay. So if we plug all those back in, for this one we already said frequency equals V over 2L. Well, here, frequency equals V over L. Well, here, frequency equals V over 3V over 2L. What would it be for the next one? 2V over L. Do you see any patterns yet? So this is the frequency of the first standing wave, frequency of the second standing wave, frequency of the third, the fourth, on and on and on. It's actually even easier than that.
Put whatever frequency it is on V over 2L.
So if F1 equals V over 2L, F2
is 2V over 2L.
Which is the same as this times 2. For F3, it is 3v over 2L, which is the same as that times 3. Guess what the frequency for the fourth standing wave is? 4 times, yeah, 4 times that first equation. So, in other words, frequency of the second harmonic is equal to 2 times F1. This is strings and open pipes. Yeah, we're getting there. We're getting there. F3, 3 times F1. Pretty handy. Nice little trick. So you can go right up the harmonics, and if you have a 440A as your fundamental for something, so if the frequency here is 440 hertz, what's the frequency of the second harmonic? It's math. It's early. Come on. Stretch your brains. Stretch your brains. 880. Yeah, it's 880. It's just twice the frequency of the first harmonic of the fundamental. So this would be 880 hertz. What would the frequency of the third one be?
1820.
I can't even do the math in my head. 412 plus 120, yeah, 1320? 1320? 1520? 1320, okay. So you see how easy that is. You can go right up through the harmonics, and we typically calculate up to about the 8th harmonic. Okay, here's the magic trick, and this is in your notes, you know. F2 equals 2 times F1. F3 equals 3 times F1. F4 equals 4 times F1, and we can just keep on going. So the general equation for that is that the frequency for a harmonic N, and you guys are all familiar with the use of N as generic, you know, this one, is equal to N times V over 2L. Where, you know, this is just the expression for the fundamental. So for whatever harmonic you're looking at, you multiply that harmonic number by the general equation for frequency, and you've got it. And you can, of course, back figure that and solve for length. So this is all, we're still talking about strings here. This is all about strings. But we don't always have a string. So in the case of something like, an N-struck plosive aerophone, a slap pipe. We take a piece of pipe, we whack it with something like a flip-flop, and we create a tone. We do that by creating a movement in the air in here, in this tube. Now on a string, if you recall, the ends are what? Nodes or antinodes? Nodes. Here, can we have a node on the end of an open? No. It's an antinode. So the wave that we create looks like this, metaphorically. Why do I say metaphorically? This is a sound wave, therefore, is it a transverse wave? No. But we have an antinode on each end, and this is not drawn to scale, and a node in the middle. So these would correlate to a compression. Actually, it would probably correlate to what? A compression here. And rarefaction here. I'm not 100% sure on that. I'm going to have to look at that. That would be my guess, because you're compressing the air at the top.
On all like open end tubes, is it always only creating like one wavelength, or not at this point actually a half wavelength? Or
well, let's do the math here real quick. So let's lay this on its side and redraw. Okay, so where would we have to go to finish this wavelength? Well, out here, right? So now we have a complete wavelength, yes? Okay, hold on. Okay, so you've got a full wavelength this here. So you're going from
Is that a blue?
middle, that's bluish,
I was making sure I
up
wasn't
to the
going
top,
nuts.
down and back to center. There's a full wavelength, but there is your pipe. So what's the relationship between the length of the pipe, open-end pipe, and the fundamental? So yeah, F1 is equal to, or I'm sorry,
That is a great color.
it is.
It's like baby.
Okay, lambda for the first, for the fundamental, is equal to what? 2L. Hey, guess what? It's the same as a standing wave on a string. It's the same mathematically as a standing wave on a string. The only thing you're changing is the fact that at each end you now have an antinode versus a node. Mathematically, however, it is identical. Okay? It just, the conformation of the wave changes. And again, I'm going to remind you every single time we draw this, sound waves are not transverse waves. We draw them that way so that our puny little human brains can cope with them. Okay? It's hard to visualize it as a longitudinal wave.
Why does...
So, let me clarify something that I did not understand in previous years. This is not the math for a struck pipe. This is not the math for a pipe where you take some sort of hammer device and you strike it. Okay?
Like what we did.
Like what you did, like a xylophone, like a wind chime, like a tubular bell. This is only the math for a pipe which is end struck. So a slap pipe, okay? So this is the math for slap pipe tubes. Or a tube where you are blowing through the tube and creating a vibrating column of air, like a clarinet, like a flute, like a saxophone, like a trombone. These are all this math. If you are striking the middle of the pipe, it is a different kind of math, and we're going to talk about that tomorrow. Because your wind chimes are not this set of calculations. I always thought they were. Who knew? Now, here's how those look. And you've got this in your notes. Whoops, didn't mean to do that. You have this in your notes, but we'll redraw it because you will be asked to redraw it again and again and again, of course. So, first, the fundamental, first frequency. Let's see, can I do this? Yes, I can. Second,
Question is, can you do the
harmonic.
What's your second?
Mm-hmm.
Just making it up. This is not real.
Third
This is not
harmonic.
real.
So, if you're struggling conceptually to see the lengths, the relationship of length of pipe to wavelength here, let's look at, so we know that for this first one, lambda 1 equals 2L, and we drew that. For the second one, lambda 2 should equal what? L. Well, does it? Let's test this. We'll go back to our chartreusey.
Yes. It's got one and then two halves.
Because here yeah, exactly. We have one full one and two halves on each end. And if we go to the next one, this should be what? 2/3. Let's test it. Whoops. And we've got 2/3 of the length of the pipe. So they're a little bit harder to visualize than the ones on strings because we conceptually deal better with nodes at the ends.
Yeah, but it's really easy to know which one.
Okay, so if we're going to look at the harmonic series for open pipes, guess what? Mathematically, it is the same as a string. So the frequency, whoops, the fundamental is equal, the wavelength of the fundamental is equal to, frequency of the fundamental is equal to V over 2L. The second harmonic is 2 times V over 2L, or 2 times F1.
Is that what you mean by the lower and higher harmonics that cause the undertones?
Yes.
Because multiple things are going to equal the same length. So when you hit it, you're going to get higher and lower tones than what you. In the loudest tone.
We'll get there. We'll get there. But mathematically, and you can keep going. You can go up, the 10th harmonic, the 23rd harmonic, though we don't really see those. In a wind instrument, so here's a very primitive kind of flute, like a recorder, where it's not got a whole lot of fancy keying. All you have is a tube with holes in it. I think you all probably had to learn to play recorders in the 4th grade or something.
Oh no,
Second grade. When you play something like a recorder, not that any of you would ever do that because clearly it's a horrible thing, as you cover up these holes, if you have all these holes covered, you are creating your wave in the entire length of this pipe. If you uncover a hole, you are now only creating a wave in that length of pipe. So what you're doing is changing the length of the pipe when you open and close the finger holes. If we cap one end of the pipe, how does that change our wave?
Well, it kind of stops.
Well, in our open pipe, we had an antinode at both ends. So we could still have an antinode here. This is open. Could we have an antinode there? No, we could not. And so what we end up with, that's going to be really hard to see, is a wave that looks more like this. So it's a quarter of a wavelength. So the wavelength for a closed pipe for the fundamental is actually 4 times the length of the pipe. Because to get a whole wave in, we would have to go out here and then again. So this is only a quarter of a wavelength.
Which means if you want 10%.
So if we want to get our second harmonic, is it going to be 2 times that? This is my question for you. Is it going to be half of that? Is there some other relationship? So remember, we're always going to have a node here. So if we do this, or an antinode here and a node here, if we do this, then what's our relationship of length to wavelength? Well, it would be out here, right? I know. I'm trying to ignore him.
I'm trying to think. And it's not happening. My brain doesn't want to think.
That would be the second harmonic.
1, 2, 3, 4. It's the next wave that we can create.
So you can't create. Oh, so you
It's the next standing wave that we can create in a closed end
So you
pipe.
create a second harmonic?
You can't create a second harmonic.
Well, that's interesting.
You jump straight to number 3. You jump straight to number 3. So on this, lambda equals what? 1, 2, 3, 4 thirds L. So this is the second wave that we can create. And the length of that wave is 4 thirds the length of the pipe.
That's fantastic.
Okay.
Which harmonic?
We only get odd harmonics in a closed-end pipe. So, if we go back to our F equals V over 4L, which is our fundamental in a closed pipe.
Which means in the end they would sound better, wouldn't they?
Well, it's a different,
Because they would have
there are not as many,
overlaying.
yeah, there are not as, it just changes sound quality. And again, I'm not enough of a musician to give you a whole lot of background all of the implications here. But yeah, it's different because you have fewer harmonics sort of working together to create the sound. So the next one we can create is actually the third. And that is
Just divided by 3.
3 times F1. What's the next one we can create? The fifth. 5 times F1. We cannot create any even-numbered harmonics in a closed pipe because of that requirement that this end is always going to be an antinode. Okay. And that slide just reiterates that. So for a closed pipe, and remember this is not a struck pipe, this is a wind-blown pipe, like a flute. Closed pipe system, we have F1 equals V over 4L. F3 is 3 times F1. F5, 5 times F1. Okay, and you'll be able to draw all of those, I'm sure. And this just reiterates what we just talked about. In a closed pipe, you only get odd-numbered harmonics. The general equation for closed pipes, Fn equals n times V over 4L. So if you remember this basic portion here for closed pipes, it's pretty easy. You know, and it does mean that you can use a much shorter pipe to get a deeper tone in a closed pipe than you can in an open pipe. And a lot of musical instruments are closed pipes, so, or roughly. If you think about the trombone, it's closed effectively on one end by somebody's lips. If you think about the trumpet, it's effectively closed on one end. Modern flutes are closed on one end. Primitive flutes are open on both ends. It's a piece of reed with a hole cut in it, and you set a vibration in the pipe, and you create a sound. But I think they're a lot harder to play, too. Okay, this is the kind of problems that you'll have on 498 and 499. And, okay, here's our sample problem from 498. Give me the first 3 harmonics on a 2.45 meter long, open at both ends pipe. And the book has us use the velocity of sound and air as 345 meters per second. We have our length, so this is really plug and play. F1 equals 345 meters per second over 2 times 2.45 meters. Okay, what do you get for a raw answer?
71.02040816.
I'm getting 70.40816, etc. Okay. What are
345.
2.45? Yeah. What are our units here?
Those 248.
What are our units here? Hertz. They're 1 over seconds, which is hertz. So with 3 sig figs, we get 70.4 hertz. Now, to find the second, we just take 2 times that. We get 140.816, etc. With sig figs, that would be 141 hertz. And I think you can probably find the third harmonic on your own. Okay, your problems on 499 are going to be just like those.
Oh, that's good, because I was really confused.
Okay, so.
Does that mean we get time to work on the homework?
I have to work on later.
So, now we're going to talk about sound quality, which the musicians in the audience, instrumentalists, vocalists, have been thinking about, I know. When you have any vibrating object, you're not just going to have the fundamental frequency happening. You're going to have additional vibrations happening. So the second and the third, you get all kinds of interesting interference patterns between them. And if you remember back from doing interference lines, very seldom do you get a nice, neat wave with interference patterns. You get little jaggy bits and things like that, remember? As all of those fundamentals are interfering or all those harmonics, your fundamental and your second and third and fourth harmonic, as they're interfering, depending on the material that your instrument is made of, whether it's your vocal cords, whether it's a saxophone or a trombone or a flute or a guitar string, you get different interference patterns, and some harmonics almost disappear altogether. Some harmonics are emphasized. So the sound quality is a result of all those interference patterns. They're different for different instruments. So for instance, a wooden flute sounds different than a metal flute because the vibration is subtly changed by the material, even though it's not like a struck chime where a wooden xylophone is going to sound very different than a copper pipe xylophone because the actual material vibrating is different. You're going to get different sound quality in different instruments. The fundamental is what determines your pitch. Remember, what is pitch? It's not the same as frequency, but it's our perception of frequency, right? It's our brain's sort of computation of frequency. So we're going to get some oddball, unique wave pattern. The fundamental will determine the note that you're hearing, but then all those other harmonics come into play and give you the overall sound quality. And people who are real musically inclined very often talk about the color of a sound. This is one of the last concepts we're going to talk about. This is beat waves. This is what happens if you are harmonizing with someone and your tones are just a little bit off. You will hear this wah, 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 in your tone. What is happening is, and let's actually, we can't blow that up. We take this wave, we take this wave. They are slightly off phase with one another. So you don't get that really wacky interference pattern. What you get is constructive, destructive, constructive, destructive, constructive, destructive. And if we look at that overall, what we end up with is this tone. Remember that amplitude is most closely related to loudness. So you get increasing and decreasing loudness. And because the constructive and destructive interference patterns, and this is shown in your notes, creates this changing amplitude. So the sound goes and comes and goes. And it's this sort of, it's maddening to a lot of people. You can actually figure out how far apart the two tones are. If you count how many, these are called beats, so this is a beat note. If you count how many times it comes and goes per second, so counting how many times it comes and goes per second will tell you how many cycles per second those two tones are apart in frequency. So if we play a 246 hertz tone simultaneously with a 248 hertz tone, we are going to hear 2 beats per second.
Is there any way to demonstrate this?
Yes, and we're going to. Okay, so the math could not be much easier. And you don't typically hear beats if you're about 5 hertz apart or more. They have to be pretty close. So about 5.
This is the same as like the beat you feel.
It's not the same as the beat you feel, but it perceptually it comes across that way. We get that sense of a beat, and that's why it's called a beat. So we'll hit a recording of this. Questions, comments, concerns? You got this? Okay. On that note, that's chapter 13 notes. So I'll give you some time to work and we'll answer some other questions.